Welcome to the HPC Best Practices webinar series, which is brought to you by the IDEAS Productivity Project, which in turn is part of the Exascale computing project of the United States Department of Energy. This webinar series is a collaboration that involves the computing facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Mosny Marcus from the Lawrence Berkeley Lab, and Ashley Barker from Oak Ridge and I will be the hosts for today's webinar, an overview of the RAJA Portability Suite, and the webinar will be presented by Arturo Vargas from Lawrence Livermore National Laboratory. Arturo is a computer scientist in the Application Simulation Quality Division at Lawrence Livermore. He completed his PhD in Computational and Applied Mathematics at Rice University in May 2017. Arturo's work focuses on portable programming abstractions, high-performance computing, and high-order finite elements for hydrodynamics applications. We have issued 160, actually more, tickets for this webinar, and all attendees have been muted. We'll be receiving questions through the Zoom chat and also the Google Doc. I have already pasted this address in the Zoom chat, but I'll do it again. And the webinar will have breaks so the speaker can respond to the questions that come in. With this, Arturo, I'll stop my sharing and you'll take over, please.
All right, well, thank you so much. Let me share my screen here. Okay, can everybody see my screen?
Yes.
Okay, all right, thank you so much. Yeah, so I'm here on behalf of the RAJA Portability Suite team to provide an overview of the different technology we've been developing. The RAJA Portability Suite is a collection of modular open source tools for developing single source portable codes. There are 4 main projects, and throughout the talk, I want to give a little tour of each of them. So there's RAJA. This is an abstraction layer for developing portable kernels based on loop level parallelism. There's Umpire, which is an API agnostic tool for memory allocations on, say, host and device, and you can do very intricate operations such as creating memory pools. There's CHAI, which is an array-like object which automates moving data between host and device, giving the look and feel of CUDA unified memory. And then there's CAMP. This offers low-level metaprogramming methods focused on HPC compiler compatibility. And all of our projects are hosted on GitHub, so folks are all welcome to grab a copy and play around with it. So the RAJA Portability Suite has been adopted by a number of different projects. And then on the slide here, I want to highlight some of the ECP projects that have successfully adopted RAJA, Umpire, CHAI, or a combination of into their code. And they've been using this technology to run on a variety of different platforms. So as examples, there's the Livermore ATDM application code. So this is a high order L hydrodynamics code. There's GeosX, this is a geomechanics code. There's EXA-SGD or power grid optimization simulations. And then there's ECP, there's SW4, which is a code for simulating earthquakes. So these codes have run on different platforms, for example, Sierra, Astra, and a lot of them, and these codes are on track for the upcoming platforms such as Aurora and Frontier and El Capitan. RAJA and Umpire has becoming the programming abstraction of choice for most of the ASE applications. So the chart here presents a list of different projects, the main language they're written in, their kernel abstraction, their data transfer strategy and memory allocation. And one of the things we see here is that across the board, RAJA and Umpire are used across these projects. There is some diversity on how data gets transferred from the host onto the device. Some will use explicit movement, some will use unified memory, and some will use CHAI. And this is just based on code constraints and the preferences of the code teams. So starting with Raja, Raja is a collection of abstractions for loop level patterns and parallel constructs. There's support for simple complex loop patterns and executions. There's support for multiple backends, for example, sequential, OpenMP, CUDA HIP. And through Raja, there's capabilities to do loop transformations without changing the application code. So examples of this is changing loop iteration patterns, permuting loop nest ordering, as well as their support for portable reduction scans, atomic operations and sorts. And then there's additional tools in here that help improve general application performance. And I'll give examples of this. And of course, there's always ongoing work. So as a starting point, I want to introduce this Raja for all method. On the left-hand side here, we have a C-style for loop that computes a dot product. And then on the Raja, and then on the right-hand side, we have the Raja equivalent. And I want to walk through a couple key differences. So one of the notable things here is that on the right, we introduce this concept of this execution policy. And the idea of the execution policy is it governs how the code will be dispatched. So examples of this is you can have like an OpenMP execution policy or CUDA execution policy, and then the code will be dispatched through a parallel region in OpenMP or through threading in CUDA, for example. Another subtle difference is the introduction of this dot object here. So this is a reduce sum object. And the reason that this is introduced is when we're doing accumulations in threaded environments, we have to be careful that we're not overwriting our data. So this reduce sum object will take care of any race conditions for us and make sure that we get the right answer. And of course, there's this for all method here, and this is our generalization of the for the for loop. So a little bit of details of this particular method. So the anatomy of these Raja methods is that they have four main concepts. There's a loop execution template method. That's the for part of the code. There's a loop execution policy, which basically governs how the code will be executed. And then there's this concept of an iteration space. So the iteration space corresponds to what the loop will traverse over. And lastly, there's the loop body, right? And this is encapsulated inside a C++ Lambda expression. Okay, so at this point, I want to pause for a bit and invite questions from the audience.
Keep going on. Go on, please.
Okay. All right. Well, thank you. So I want to return to Raj in a bit, but I want to introduce now Umpire and CHAI. So as I described, Raja brings loop level parallelism to applications, but when running on the GPU, we have that additional detail of having to move data between the host and the device. So CHAI is designed to complement Raja and transfer data behind the scenes automatically at runtime as needed between the host and device. So as an example of this, this code snippet here illustrates allocating arrays on the CPU. And then once a GPU kernel is encountered, CHAI will recognize this and trigger the movement between the CPU onto the GPU. The actual data movement is actually done through Umpire. So under CHAI sits Umpire performing the CUDA allocations and movements. CHAI is just there to orchestrate this. And then once the data is on the GPU, we do our calculation. And then when we return to the CPU, CHAI will recognize that data is needed back there and will move the data back onto the CPU from the device. In addition, CHAI introduces the concept of a managed pointer, which simplifies the use of virtual classes across host and device. So for example, we have an object here called shape with a virtual function called process data. Through the use of this managed pointer, developers can can seamlessly move the data between the host and the device without having to explicitly express the CUDA mem copies. So one detail about this is that this feature does require the objects to have host device class constructors. So under CHAI sits Umpire, as I mentioned. Umpire is there to perform the memory allocations to perform the moving, the copies, or whatever it may be. So Umpire has really unique capabilities. You can construct memory pools. So with a memory pool, this enables you to draw memory faster than, say, using malloc and CUDA malloc. And this is a neat tool for sharing memory between different application components. And there's also the capability of doing introspection. So through Umpire, you can ask questions such as, what is the data associated with this pointer? How much memory is the data using? What is the size? Questions of that sort. And the beauty of Umpire is that it provides a simple API for managing memory from different implementations and hardware. So by using Umpire directly, developers can easily maintain fine-grained control of how memory is allocated and specific memory movement details. The Umpire API is simple and only has 4 core concepts. There's this concept of a memory resource, which specifies what kind of memory is being allocated, memory allocation strategy. So through an allocation strategy, you can choose from allocating from a pool, using an allocator that's thread safe, specific algorithms for particular allocations, et cetera, et cetera. And then there's the allocator. So with the allocator, this is how you do your allocations and freeze. And then there's this concept of an operation. So the operation is the action you do with particular data. For example, copy, move, sending the data to a value. And these concepts are all coordinated by this resource manager. So earlier I mentioned that Umpire memory pools may be used in a large multiphysics code to coordinate device memory sharing between physics packages. And to illustrate this, I want to consider a physics code A with 2 packages A and B. We can also call them states. So in a typical application, there tends to be a loop between the different active physics. There will be an A phase and a B phase that are separated by some time step. And without the use of a memory pool, one may be tempted to have each of these states allocate their temporary memory and hold on to it throughout the course of the simulation. But this really limits the amount of memory you can have per each state. So here on the right, here's an example of using an Umpire memory pool. And with the Umpire memory pool, we have the capability to create a generic pool where each state can take turns using the pool, drawing to and from the pool. So for example, in the A phase, the A state is free to use all of the memory. And then when it's done with it, it can return the memory back onto the pool, and then the B state can take over and use the memory. So just as a quick summary of Umpire, Umpire is an API for general memory management. It's composed of very intuitive concepts. It supports various memory types, for example, host, GP, global, pinned, unified memory, and it's very, it offers features that are very useful in HPC applications, such as creating these memory pools, doing these queries, providing thread-safe allocators, and memory introspection. There's native interfaces for C++, C, and Fortran, and there's a lot of useful tools for debugging, such as logging and backtracing. And you can also replay the different memory allocations that you've performed through Umpire. Okay, I want to take a little short break. Any questions?
Yes, I see a question here. I think the RAJA team has been answering some of the questions as we go, but there is one here. How does it work for nested loops?
Oh, that's the next part of our talk, actually.
All right. Okay.
But
Yeah,
I'm happy. Yeah, I'm happy they're asking. Yeah.
All right. Okay. Please continue then. Thank you.
All right. Yes, of course. Okay. So returning to RAJA, I want to introduce 2 APIs for nested and complex loop kernels. So we started the discussion on RAJA by introducing loop level parallelism for a simple loop, but for nested loop patterns, we may want some flexibility and you maybe expose more parallelism. So to kick off this discussion, I want to use this matrix multiplication example to explore some of the RAJA features and usage. So the example I have here above is a simple matrix multiplication kernel, and multiplies two square matrices A and B and stores the result in C. Building from the for all methods, we may be tempted to replace the outer C loops with RAJA with for all methods. However, the issue here is that the for all methods treats each loop level as an independent entity, meaning we can parallelize each level of the loop, but one of the levels would be running sequentially. Additionally, if you want to do like loop interchange and other types of code transformations, that would require source code changes, which breaks the RAJA encapsulation model. So for this reason, we don't recommend using RAJA for all methods for nested loops. But one option in RAJA for nested loops is to use the RAJA kernel API. The RAJA kernel API is designed to compose and transform complex parallel kernels without changing the source code. So how the code will be executed is expressed in a particular policy, as illustrated here above. And this policy will typically live in a header file. And then in your source code, you would have the collection of loop bodies. So to help introduce RAJA kernel, I want to make some analogs between standard C code and how you would express this in RAJA kernel. So here on the left, we have the two outer for loops from our matrix multiplication example. So to express this using RAJA kernel, you would express for loops as these statements. And then for each for loop, you have an associated policy that will essentially dictate how the for loop will be executed. And then for each level of the loop, you have to have an associated iteration space. The integer value here corresponds to which iteration space in the tuple is associated with that for loop. So performing loop transformations using the RAJA kernel API is pretty simple, as the policy controls how each loop level is executed. So in the example here, but in the slide, we have the outer loop being the row loop and the inner loop being the column loop. And if we want to do loop interchange, you just switch the order of the statements. So here, the result of this is that the outer loop is now the column loop, and then the inner loop is now the row loop. So then to actually invoke the loop bodies, Lambda statements are used in the execution policy to invoke the Lambda. So here in our policy, we're saying we have two for loops, and then we have a Lambda statement, which executes the actual work. The Lambda is, the contents of the Lambda are held here in this kernel method. And as you can see, the loop body is exactly the same as you would have in the standard C code. So just as a quick summary of the RAJA kernel capabilities, this kernel API offers numerous options to explore execution alternatives and optimization strategies. There's things like tiling statements. So these are, this is a technique that takes an iteration space and breaks it up into tiles. And this can ensure that data stays in fast memory while it's being used. There's access to portable kernel local memory. This would be CUDA shared memory on the GPU using NVIDIA, or stack memory on the CPU. There's capabilities to do loop interchange via execution policy change, as we saw earlier. There's also support for things like loop vision and fusion. And then when it comes to GPU programming, there's a variety of policies to help map loop iterates to GPU blocks and threads in different ways. Okay, so another way to express nested loops is with RAJA is through the new launch API. And I want to point out that this is now available. It is marked as experimental, as we're still refining the API a bit, but RAJA launch works differently than kernel, as it creates a kernel execution space for developers to write in. So as a quick overview, there's three components I want to highlight here. There's this launch method, and then this launch method sets up a kernel execution space for host or device. So you also have a runtime selection of running the kernel on the host or the device based on the value here, execution place. So the job of this launch method is just to create a general space for folks to write their code in terms of these nested loops. There's also this launch context. So the role of the launch context is to control flow within a kernel. So the launch context can be used to perform thread synchronizations. And I do want to highlight something about the capture types. So in the execution space, we have this outer lambda, which captures things by value. And it's designed this way to make device copies of captured variables. Once you're inside the actual execution space, your loop methods will take lambdas to capture by reference. And the reason we have it this way is to enabling referencing within the loop hierarchies. So to further explain the this RAJA launch API, I want to make some analogies between standard C loops. So within the kernel execution space, developers can express their loops within the execution space through these loop methods. And this is different than how we would do things in kernel, as we're now encapsulating the loop hierarchy in the execution space. But anything that you would express in terms of for loop would simply become a RAJA loop method. And of course, the loop body just transfers over, right, and everything stays intact. For GPU execution, we try to follow the same programming model introduced by CUDA and HIP. We have the notion of teams and threads, which is equivalent to CUDA and HIP blocks and threads, right? And for this reason, sometimes we'll call this API RAJA teams. So loops can be mapped to either teams or threads using these loop methods. And then when running on the CPU, these loop methods will fall back and be executed as standard C loops. So just to illustrate on how computing with teams and threads works, it's basically the same thing as you have in CUDA, where you have a compute grid composed of threads, and then they get grouped into blocks. Same thing here. So with this configuration, we have 3 teams composed of 3 threads, and this is how we would do our calculation in a GPU kernel. So like other RAJA constructs, policies are used to choose how the code will be executed. The launch and loop methods differ to other RAJA constructs, as they now take both a host and device policy. And by taking both a host and device policy, this enables the API to have 2 versions of the code ready, so developers and users can choose between running the code on the host or device at runtime. So this is illustrated here on this particular slide, where we highlight the different policies. And then for the policies, for example, for the launch policy, we would provide a host or device, and likewise for the row and column, which dictate how the code would be executed. Currently, we have support for sequential on the CPU, OpenMP, and then on the device, we have support for CUDA and HIP, right? And as we're developing our code, you can mix and match whichever policies you want. So for the next set of slides, I want to just make some comparisons between how matrix multiplication can be expressed using CUDA and RAJA team semantics. And of course, throughout my slides, I want to also report the runtime to give an idea of what kind of performance differences might be observed when using this RAJA teams or launch API. So one way to perform matrix multiplication is to consider a 1D compute grid of both blocks and threads, and choosing to map the rows to blocks directly, and then for the columns performing like a grid stride loop, and then performing the dot product. So the RAJA analog of this is just to actually ask for this threading strategy through a policy. So if you want to map things directly, you just use these direct policies. And then if you want to perform loops, like we see on the left-hand side with CUDA, you just use these loop methods. And then you express your code just in terms of nested loops. Just to illustrate the difference in runtime here, this was actually a surprise for me, but we actually found that the CUDA version, the RAJA version was slightly faster. I don't have a good explanation for this, but it was a nice surprise. Another approach to perform matrix-matrix multiplication is to consider a two-dimensional grid of threads, and then use these threads to perform dot products. So this would require calculating global indices. So say I want to map the rows to the global thread index in the Y dimension, and then the column to the global index in the X dimension, right? So that requires doing this type of calculation. The RAJA analog of this is you just ask for the global thread. You can do it for the X and the Y accordingly. And then something else I want to point out is that when you're doing the calculation in CUDA, you would have to do these bounds checkings, but we wouldn't have to do that in the RAJA variants because these loop methods actually take care of out of bounds indexing for you, right? So these loop methods make sure that we're only indexing within the row and column range accordingly. And again, I'm reporting the runtime here, and then we found that for this value of n, the performance was within 2% of the native CUDA implementation. Okay, so this is a more intricate example where we're using shared memory and we're loading data into shared memory to do the matrix-matrix multiplication. It is a busier slide, but what I really want to point out is that I think the features such as shared memory and thread synchronization also exist in this RAJA launch API. So to do shared memory CUDA, we would just use this shared annotation. The analog in RAJA is just to use this RAJA team shared decorator. And this will do the right thing when you're running on the CPU as well. This will just be a CPU stack memory. And then this particular algorithm requires thread synchronization. And as I mentioned before, we can use the RAJA launch context to perform synchronizations within teams of threads. So to do that, we would just call it a team sync method. And lastly, the runtime. The runtime here is within 5% of the native CUDA implementation. Okay, so here I want to take a quick pause. Is there any questions that I can answer?
We are good. There are questions coming in through the chat, but Rich has been taking care of them. Please
All
keep
right.
going. Yeah.
Thank you so much.
It's a real time.
All right.
Hi.
Yeah. All right, awesome. All right, so more than a basic loop abstraction layer, RAJA provides other mechanisms to improve application performance. And I want to give a quick tour of some of these capabilities. So one of the newer features in RAJA is the ability to do asynchronous kernel execution with RAJA, CHAI, and Umpire. And as an example here, for folks who are familiar with CUDA streams, we can create different CUDA streams using this RAJA resource tool. And by creating CUDA 1 and CUDA 2, we're essentially creating two different streams, or we can launch kernels, and the work will be done independent of each stream. So just an illustration of the mechanics of this, we can supply our for all methods with these resource objects and then treat them as events. And essentially, by treating them as events, we can create a queue of activities for the streams, and we can also use these wait methods to orchestrate how the kernels will be executed. For example, here we instruct stream 1 to wait on event number 2, which happens on a different stream. And of course, this can be integrated into your existing RAJA code. You can have your for all methods just specify on which stream you want to have them act on. And whenever we encounter activity on the CPU, we make sure that all the data has been executed and is available for computations on the CPU. RAJA also has an API for fusing kernels, so they are executed within a single kernel launch. So this is a very useful feature for applications who have to do packing or unpacking of Halo data. So one approach, which is a less efficient approach on the GPU, would be to consider different fields that you have to pack, and then packing each of these fields into an API buffer in different kernel launches. So here we're doing multiple kernel launches to pack our MPI buffer. We found that a more efficient way of doing this is having a single kernel launch that does all of the packing for us. This approach is very useful because it lets us overcome this kernel launch overhead that we see with very small kernels. As an illustration on how this would be done without kernel fusing, the code on the left illustrates what a typical application code may do. So for example, for your different MPI neighbors, you would loop over your different fields. And then when you're doing the packing, you would be performing all of these kernel launches. So you're doing the packing on the GPU. And then you would send all the name, then when your MPI buffer is packed, and then you would send the data. The more efficient approach through RAJA would be to use this RAJA work pool object. And so this lets you essentially create a queue of different kernels that you want to invoke in a particular kernel launch. So we create a list of kernels. And then when you're ready to actually launch the kernels, you invoke the run method. And then rather than invoking multiple kernels, they all get packed together. And then in a single kernel launch, all of the work gets done. And then once you do that, you're free to send the data through MPI. So this is a technique that's helped a lot of the application codes improve their performance by 5 to 15%. So as we're developing the RAJA API, we're also fairly mindful of potential overhead we introduce. So to monitor potential performance overhead, we use the RAJA RAJA Performance Suite. And this is a tool that we use to look at compiler performance and collaborate with vendors. So anything above the line is a speed up that we see when we're using the RAJA variants, and then anything below would be like a slowdown. The key takeaway here, though, is that for a variety of different kernels, the RAJA performance stays within 10% of almost all of the suite, all of the kernels in the suite. And lastly, the RAJA launch, or the Teams API that we introduced earlier, was code developed with one of the Livermore applications, the Marble team, to be more exact, right? And this is an API that was developed to target more the kernels that come up in high order finite element applications. And in developing this API, we worked with the MFM team, and we looked at a fairly optimized CUDA implementation. And the plots here illustrate performance for the throughput performance for a particular finite element kernel. The different lines correspond to the different orders. And of course, higher is better. So through iterations and working with them, we were able to refine the RAJA Teams API to essentially provide on-par performance to a CUDA native CUDA implementation. And of course, with the RAJA Teams variant, we also have the CPU implementation as well. So I really want to highlight some of the accomplishments that the ECP applications have been showing through their adoption of RAJA, CHAI and Umpire. And I want to highlight some of the speedups that the different teams have been reporting. So the Livermore ATDM application, the high order L hydrodynamic code, this is a code that uses RAJA and Umpire, and they've been reporting some really good speedups on Sierra. So Sierras are the GPU machine. They've been reporting the 15x speedups versus a commodity system. And they've also been reporting 30x speedups on Sierra versus Astra. So this is an example of an application code that also integrates with a math library. Another example of how we work with teams with application teams to add new capabilities into Raja. So a second example of an ECP application is SW4, right? So SW4 is used for high resolution earthquake simulations, and this is a code that uses RAJA and Umpire. So they've been able to achieve 16 and 32x speedups on Sierra compared to commodity systems. Their work has been highlighted in the Bulletin of Seismology Society of America. And this code is on track for running on AMD and Intel GPUs. Another application I want to mention is GeoSex. This is a code that uses RAJA, Umpire, and CHAI. And through some hard work, they've been able to achieve some really good speedups on Sierra. So they've been reporting 14x speedups on, well, I should clarify, they're running on LASN, but this is essentially the same architecture as Sierra over a commodity system. And they're on track to be running on thousands of GPUs on Summit. And then an application that most recently adopted Raja is the Exascale application. So this is a code that looks at this power grid optimization. So they integrated Raja and Umpire roughly 8 months ago, but within that time frame, they're now showing that their key kernels are running at near peak memory bandwidth with very little specific tuning. And they have parts of their code running on Tulip, which is a frontier early access machine with good performance. Okay, is there any questions I can answer?
No, I think you can continue, Arturo, because
All right, thank you.
things are going well here in the chat. Thank you.
All right, awesome. So the theme here is really what drives the development in Raja is very much the needs of the application, right? We work with large integrated codes with many modular packages, and we acknowledge, we know that these codes have to run on a variety of platforms and are under continuous development. In working with these applications, we found that the RAJA Portability Suite enables applications to be portable and high performance. It enables code projects to keep programming specific concepts out of their source code. But we found that Raja is very flexible, and our code design approach has led to very nice outcomes. In particular, people are finding that Raja is easy to leverage, easy to grasp, easy to integrate, and easy to adopt incrementally, which is very important for codes that are under continuous development. We also, as I mentioned, there's been a lot of work that has gone into these applications to make them performant, and it does require a good plan, right? Some of the things that we've been learning is that developing a plan is really important, in particular making sure the plan is agreeable to all developers, understanding the meaning and how to manage portability, right? Like how much of the code needs to change. Choosing the memory management strategy. We saw that different code projects take different approaches, right? And this could be because of the constraints of their code. Some things we've also learned is that what's really important is data structures and how you're accessing the data. We found that it's best to keep the code clean and data access as simple as possible. There's also approaches where folks were like to maintain a particular field to the code. So folks will introduce a code-specific wrapper around Raja, and this helps them create more of a domain-specific languages. It's also important to establish good performance expectations. So what this means here is understanding your kernels. Are your kernels going to be memory bandwidth bound? Are they going to be compute bound? What are the appropriate types of optimizations that can be made? Of course, it's it's best to always try to port some code, analyze performance, and then optimize as needed. And this is very much an iterative process. We highly recommend continuously monitoring performance, right? If you have a CI process, you can make this part of your as part of your process. Something else that we've learned for good performance on GPUs is to keep the data resident on the device. Too much memory, too much movement between the host and device really impacts performance. And then we also highly recommend doing focus optimization efforts. So taking the code, understanding where most of the time is spent, and focusing the effort is there. And I'm showing all these results, but I do want to highlight that this was very much an iterative process. A lot of these teams have been working on porting to GPUs for some time now, and there has been a lot of progress, but there's always work ahead of them. So programming on these GPUs also have considerations that are typically not seen on CPUs. For example, GPUs have this kernel launch overhead. So there's also the fact that there's different memory spaces now, host and device memory, right? So there needs to be an appropriate strategy to move the data accordingly. And then GPUs tend to also have less memory than CPU-based platforms. So for this reason, we really think memory pools are a must. And then for folks who work on very integrated codes with different packages, there's a component of coordination, right? If there's packages that are unported, this will lead to costly CPU and GPU data transfers. So the RAJA Portability Suite has demonstrated utility on current architectures and is on track for future platforms. So just to highlight some of these upcoming machines, for the Perlmutter machine, which has NVIDIA GPUs, we have the CUDA support, and the CUDA backend is actively being used on production codes on Sierra at Livermore. So we continue to investigate and improve performance for the CUDA backend. For AMD platforms such as Frontier and El Capitan, we have HIP support that's been available for some time. And then for the Aurora machine, which has Intel GPUs, we have the SECL backend in current development. And this is collaboration with Argonne, and this is part of an ECP project as well. But the support for Umpire for Intel GPUs is there now. So I do want to mention that we are fairly active. We have over 38 contributors, and there's 8 core team members. We also stay engaged with vendors, and we stay up to date with the newest features and capabilities. We also participate at conferences, ECP meetings, all sorts of things. And just to start wrapping up, so why use portability solutions like RAJA, Umpire, or CHAI, or should you? Well, the answer is it depends, right? It does require understanding or having a grasp of what performance portability means for your project. If you have a very small code base and you're interested in the best performance ever with very specific programming model features, then you may prefer to rewrite the code with the different programming models. But if you have a large application with various contributors, portability solutions like this is really the way to go, right? A portability solution like this will enable you to write a single source code that runs on a diversity of platforms. Some of the benefits of a portability solution like this include that you no longer have to worry about platform specific code, right? We can essentially eliminate that. It's also easier to separate software development concerns from your project. You can create abstraction layers, so folks who are more interested in developing physics can work on that, and computer scientists can focus more on the fine-grained optimizations. And you also leverage the expertise and efforts of the other folks, like for the folks who work on RAJA, right? As we're making RAJA better and faster, your application will definitely benefit from this just by updating your RAJA package. And just some links to help people get started. There's user guides for RAJA and Umpire. There's templates available through GitHub. There's a performance suite that's also on GitHub. We have proxy apps. And then also just a small plug for CARE. And CARE is a project that expands on CHAI and RAJA, and it adds additional capabilities for folks who are interested in building on CHAI and RAJA in their application. And of course, for any questions and support, please email us at rajadev@livermore.gov. All right, and with that, I conclude. And if there's any questions that I can answer, I'm more than happy to.
Okay, thank you, Arturo. Very nice, time-wise even. I think I'd like to tell the participants here that we're going to take all the questions and answers in the chat and consolidate them and do some cleaning and put in the Q&A document that we'll send to you maybe early next week. But Arturo, to give you an opportunity to answer some of these questions here, let me go to the bottom here. Let's see here. I'll take this one here. What is the difference here between other approaches, for example, COCOS?
The approach here is that this is more modular, right? You can pick and choose which components you can add, you want to integrate into your application. And then for some of the nested loop capabilities, you have more fine control of how you want to map loops into threads and blocks and into GPUs and things like that. So I would say it's a different approach to solving the same problem.
Okay, so what I just did here, so participants, if they would like to ask a question, but I just, participants can unmute themselves now if they so wish and ask questions directly to Arturo. Let me go here and see if there's any other here. Let's see. Okay, let me pick one here for you, Arturo. Aurora is an Intel machine. Intel already has one API. What are the advantages of using RAJA and CHAI in that case?
Well, the advantage is that if you use RAJA and CHAI, then you have a single code, then you can then run on, say, NVIDIA platform with a native CUDA implementation. And my understanding right now is that CUDA is probably going to give you the best performance on NVIDIA platforms.
All right, another one here for you. I'm going from the bottom, actually. Are there any recommendations for tools that measure performance that integrate with CI? Would something like Tau HPC toolkit work?
I can't speak to that particular tool, but I've used Caliper in in the application I work. I've had great experience with Caliper, so I recommend Caliper. Maybe if folks have other recommendations, they can also recommend.
Okay, folks, any other? Okay, there is one that just came in here. With the abstraction layer as RAJA, are you running into compiler limitations in specifically with NVCC, where the extended Lambda is very heavy on the symbol generation?
Yeah, so there has been compiler bugs that have come up, but we work with the vendors, and these are things we work through with them as well.
All right, so again, to the participants, you can unmute yourselves if you'd like and ask questions directly to Arturo. Any takers? As I said, we are going to take the chat and And go
Yeah,
through
I had
it.
a question.
Oh,
Better
okay.
here.
And you're
It's
Peter?
very,
Okay,
very
good.
impressive. Very impressive talk. More related to this ability to asynchronously move memory around. So does the CHAI and Umpire take advantage of that? So when you are running multiple kernels and at the same time, we always oversubscribe the GPU to some degree because the memory is more limited than on the CPU side. So is there any machinery built into these managers that can basically benefit from these asynchronous memory moves?
Yeah, so the example I showed, yeah, it's designed to be to work in conjunction with CHAI and Umpire.
Mm-hmm. And the granularity is in general on the whole array level, or do you go sub-array? So can you page in, page out the blocks that are currently being used?
The blocks, I'm not sure what you mean by that. Like the blocks of memory, or?
Right. So when typically in all these all the solvers, when the discretization is being processed, so the memory is being fed in sort of in pages. So is there anything sub-array level, or is the minimum unit the whole array, the whole mapped object?
I'm actually not sure. Rich, would you be able to comment on this? I'm not 100% sure.
I can comment on this a little bit. So this is Peter Robinson. The CHAI, for instance, is kind of array-based for bulk memory movement, but it does have like a pick capability to like pick single elements if you need to do that. But generally speaking, it's taking the approach that the whole array is what you want to deal with.
Mm. Okay, thanks. Thanks a lot.
Thank you, Peter.
Any further questions? All right, very good job, Arturo. Yes, and the folks that helped with the questions and the answers also in the chat. Arturo, I'm going to take then if you can give me the share, I'm going to share my screen here, okay?
Okay, here we go. Stop sharing.
All right. So it's just to announce again. So thank you very much for participating. We'd like to improve the series. There's the survey that I think would be helpful for Ashley and I, the organizers of the series, but also to the presenters in the webinar series. The slides and recording will be available at these two addresses. The slides are already available. I pasted in the chat where the link. So the next event in the training effort of the Exascale Computing Project, March 30 to April 1st, we have the ECP Community Birds of a Feather Days. It's an opportunity for the high-performance computing community to engage with the ECP teams to discuss the latest developments by the teams. People can register at this address. I also pasted there in the chat. And again, just to make it clear, this event will not be recorded, okay, contrary to the webinar in the series. And the next webinar in the series is going to be on April the 7th, a workflow for increasing the quality of scientific software. It's going to be presented by Tomislav Marik from Technical University of Darmstadt in Germany. And people can register for that webinar already. So with that, thank you all for joining. Thank you very much, Arturo. Ashley, do you have any final remark for?
Nope, just add my thanks to yours as well, to Arturo, and then the Herculean effort from Rich to answer all those questions in the chat. So we really appreciate getting those answers real time. I think that the attendees appreciate that too. So thank you both. And Osni, thank you for organizing.
It was a pleasure. Thank you, folks.